Okay, we're here to look at Worksheet 8 solutions on light and geometric optics, okay? I suggest you can't see what's on the board very well, just open up the solutions or have them at hand, okay? Okay, so quick questions. Provide one-line definitions of the following. This is sort of important. You should know the terminology, what's what, right? Diffuse reflection, that is when we get reflection at all angles. That's how we see things. Specular reflection, that is a reflection from a mirror, what you probably think of as reflection. Refraction is the bending of light when it passes through media where the speed of light is different. Diffraction we haven't really talked about yet. Diffraction is where light bends around obstacles. I've put it in here with this problem set because sometimes there's a bit of confusion between diffraction and refraction. Diffraction, we'll talk about that more in the next chapter. In the next chapter, we look at the wave nature of light. Instead of tracing rays, we'll be looking at light as it bends around and behaves like a wave and interferes. Dispersion is when the wave speed depends upon the frequency. If the wave speed depends upon the frequency, then so does the refractive index. So the refractive index of glass, I could say it's 1.4, but if I say that, I have to say it's 1.4 at a given frequency. Different frequencies of light would have a different refractive index, right? So glass has a refractive index value for a given wavelength, right? It does depend upon the wavelength. Interference, again, we haven't really talked about this, but interference, what we'll see in the next chapter, is that light behaves like a wave and it can interfere constructively or destructively. And say we're getting into that. Total internal reflection, this is where the light passes from a dense medium where the speed of light is slow into a rare medium where it's fast, and at a certain angle the angle bends such that it's 90 degrees and the light cannot escape from the dense material and is trapped inside. This is how optical fibers work. Chromatic aberration, well, this is with a lens. A lens brings wavelength of a particular frequency to a focus. A different frequency of light would be brought to a different focal point. So when I produce an image with a lens, the image doesn't come to one focal point, it's sort of smeared out. So if I had a piece of paper, I might see the red image at one point, move it closer, I'll see the blue image, okay? As far as telescopes go, this is a problem with telescopes, so astronomers would just put a particular filter in front of the detector, so we only see the blue image or we only see the red image. You can't really take a good image at all frequencies at the same time. Cameras get around it. They have some clever optics. A camera lens, if you look at it, is very complicated, and a lot of it is to reduce the amount of chromatic aberration. Astronomers would not want to do that because the lenses absorb a lot of light, and so it's not a good idea as far as astronomy is concerned. But in photography, there's lots of light around, so you don't really care. You make complicated lenses. Spherical aberration. This is where a spherical mirror does not bring bring everything to a focus, right? The focus point does change. If it's a very curvy mirror, you get bad chromatic aberration, but the flatter the mirror, the less the spherical aberration. I think I said chromatic aberration. I meant spherical aberration there, okay? We had a diagram in the slides which showed that effect. What did Isaac Newton invent to overcome chromatic aberration? Well, to overcome that, he invented the reflecting telescope, right? So Isaac Newton figured this out and invented the reflecting telescope. Yeah, it took a while for, reflecting telescopes took a while to catch up, but now certainly any professional telescope that astronomers would use would be a reflecting telescope, no doubt about it. Many reasons, which I won't get into here right away. Okay, in the below diagram, drawing rays that show how the stick man sees the top of his hat and his feet. And it's probably easy, I just show you the diagram. Here it is. And so we imagine a ray coming from his feet. It has to bounce off into his eyes. And here's a ray from the head, it bounces off. So these angles are equal. And if we extended that, these angles would be equal, right? So that's a ray from his feet going into his eyes, that's a ray from the top of his head going into his eyes. What he would see though, from his point of view, the top of his head, he's seeing it, it appears to actually come from over here, and his feet, we trace this ray down here. So he sees this image behind the mirror. Interestingly, if you sort of split this into triangles, let's imagine that bit there. This bit of the mirror is half of this distance, and this upper part of the mirror is half of that distance. So if you think about it, the mirror has to be half the height of the guy. So the next time you look in a mirror, to see your entire length, the mirror only has to be half of your height. You don't need a mirror down to the ground to see your entire. So you need only a mirror half of your height. Question 4 is the radar reflector. Draw a sketch to outline how the reflector works. It's a bit tricky to do a sketch, but I just really want you to look at the answer and understand this. Here's sort of the solution. I showed you this. There's a video of me by the display case with a rat and the eyes that light up. But here we have different rays coming in. They bounce around and they come out in the same way. After multiple reflections, they always come out the same way. So if you've got one of these on a ship, you shine a radar on the ship and the radar would bounce right back at the detector. Stealth airplanes, I think I mentioned here, with a stealth airplane, you want it to be invisible to radar. And so instead of having curved surfaces, they have angled surfaces. So the radar comes in and it gets bounced up. You can imagine that if you had a curved surface on a plane, part of that surface would reflect the radiation back in the direction it came. But if everything is angled, then when the radar hits it, it all bounces away in particular directions, and the chances of something bouncing back at the radar are quite slim. So when you look at stealthy planes, you'll notice, I mean, they look kind of cool and futuristic, but all that they've done, they've taken off any curved surfaces and made everything very angled on them. This, in the display case, this is called a corner reflector, and on the assignment sheet we have a problem which is sort of discussing this. These you find on boats, but the light comes in and it reflects off the 3 mirrors, which are all at right angles to each other, so it doesn't matter what angle the light comes in at, it bounces around and it comes back out in the same direction. So if you're ever on sort of sailing on a sailboat, for example, you might notice that they have these cross bits of aluminum in the upper parts of the rigging, and that's a radar reflector because they're pretty small, they're hard to see on radar, but with a radar reflector, this bounces radars right back at them. And you can see we've got our rat here, and the rat's being reflected in all these different directions. One other thing in the display case, I do have an optical fiber, and what I've done, I've shoved one end of the optical fiber up by the lamp, and then it comes along, and if you look here, this is just light coming out of that optical fiber bundle. Okay. I think that's all I need. Question 5, a solar cooker, which is a concave mirror pointed at the sun, focuses the sun's rays 18.8 centimeters in front of the mirror. What is the radius of the spherical surface from which the mirror was made? If you recall, the focal length of a spherical mirror is 1/2 of its radius of curvature. So it's going to be 2 times 18.8 centimeters, which will be 37.6 centimeters, I guess. Yeah, there we go. Easy question. Okay. Question 6, how far from a concave mirror must an object be placed if its image is to be at infinity? The way to think about this, I guess, is to think about rays coming from infinity. If we had rays coming from infinity, they would all end up at the focal point. I haven't really got a diagram for this. Maybe I should add a diagram for future reference. I'll make a note to do that. Sorry, just let me write that. Okay, so getting back to the question, imagine the rays coming from infinity. They come into the mirror and they come to the focal point. Well, now imagine I had something at the focal point. If we trace the rays backward, they would go off to infinity. So the answer to the question is that the image would be at infinity if I placed the object at the focal point. Okay. When you think of a spotlight, you need a nice solid beam of light. What they do with the spotlight is to have a mirror, a concave mirror, and they put the bulb at the focal point, and so it goes out as a beam. It doesn't diverge out or diverge in and then diverge out. By putting the filament, the light source directly at the focal point, you get a nice beam of light coming out of it. What type of mirror is shown in figure 2? It's a shiny one. No, okay. It's convex because the image is smaller. It appears smaller. That's the answer. If you look in the wing mirrors of a car, it says that objects in the mirror appear smaller than they really are. Okay, and so this allows us to see more of the road. So figure 2 would be showing a convex mirror. Is that right? 7 convex. Yes. Okay. Question 8. The speed of light in ice is that value. What is the refractive index of ice? Remember, refractive indices are always larger than 1. So do I divide by the speed of light? Which way around is it? I need a number bigger than 1. So I need 3 times 10 to the 8 over 2.29 times 10 to the 8. So that would give me 3 over 2.29, about 1.31. Okay? If you ever get a refractive index less than 1, something's gone wrong. Okay? Question 9. A diver shines a laser pointer upward from beneath water at a 35-degree angle to the vertical. Well, what angle does this light leave the water? So again, I'll try and do a diagram with these, otherwise they get a bit confusing. Here's the water, here's the light coming up, and this is the dense medium. So imagine again the Romans marching along. This Roman soldier gets out first, so he speeds up, and the others take more time, so it bends around like that. I know N1 is the refractive index of water, N2 is the refractive index of air, which is around 1. I got theta 1, theta 2. What I want is theta 2. So here's a Snell's law here. I want theta 2. So I can quickly solve this for theta 2. There's the algebraic solution. And then just slug in some numbers and out pops the answer. Question 10. An aquarium filled with water has flat glass slides whose index of refraction is 1.54. A beam of light from outside the aquarium strikes the glass at 43.5 degrees. So here's my light coming in, strikes the aquarium at 43.5 degrees, right? Here's the normal, here's the glass, here's the water, okay? What is the angle of the light wave when it enters the glass? Well, I've got theta 1, theta 2, I've got N1, I've got N2. So I can quickly work that out. Theta 2 is essentially the same that I've done up there. I've just got this equation and I'm reusing it with some different values. So that would be 26.6 degrees. The light then goes from the dense medium to the rare medium, so it bends back around in the water, right? So it slows down going into the glass, so it bends that way, and then speeds up slightly when it comes back into the water. So again, if I want this angle, in this case, I've got N2, N3. I've got N2 is my glass, N3 is the water. I've got the angle of incidence, so the angle at which it comes out at is 31.2 degrees. That would be that angle in there. I haven't labeled the angles. Maybe it'll be hard to add labels for those angles, but maybe I'll try. I'll make a note to do that. It might be a bit hard to squeeze them in. The third part asks, well, what if we hadn't had the glass? What would happen then? Well, in that case, I've got theta 1, N1 is air, and then N2 is water, and I want this angle here. So solving for that, I've got N1 over N3 this time. I put the numbers in, I get 31.2 degrees. Well, that's interesting because you can see it's as if the glass wasn't there. These are the same. So the angle, the angle in the water is as if it comes straight from the air and it hadn't passed through the glass. Okay. Question 11, what is a critical angle for the interface between water and crown glass to be internally reflected, the light must start in which material? Okay, so here's the diagram. Remember, if this is glass, what we need it to do as it comes out, it needs to bend around like that, right? So it needs to speed up as it comes out of the material, because it needs to go in that direction. So it must be that the light starts in the glass and we have water around it. Imagine if this was water and that was glass. As it came out, it would bend in that direction, right? It would bend like that. We need it to bend like that. So it must be glass here and water there. We're told that this angle is 61 degrees, and what's the question? No, we're not told that. What is the critical angle? We want that. Well, in that case, we've got n1 sine theta 1 equals n2 sine theta 2. But for total internal reflection, theta 2 is 90 degrees. n1 I know, that's the glass. n2 I know, that's the refractive index in air. So I need to solve this equation for theta 1. And when I solve it for theta 1, I get 61 degrees. And I guess 61 degrees was put into the diagram. Okay? I might change that to theta 1. Yeah, Okay, question 12. A beam of light is emitted 8 centimeters beneath the surface of a liquid and strikes the air surface 7.6 centimeters to the right from the point directly above the source. If total internal reflection occurs, what can you say about the index of refraction of the liquid? So again, I think it's worth doing a diagram. Here's our light source 8 centimeters below. It comes up, it strikes here, and we have a total internal reflection. So very quickly, I can work out from a simple geometry what this angle is here. Tan of theta, hang on, I need, that's the normal, I need that angle in there. So the tan of theta will be equal to 7.6 over 8, 43.5 degrees. And then my second angle would have to be 90 degrees. Here's Snell's law, n1 sine theta 1 equals n2 sine 90. n1 then, what would I need for n1? Well, n1 is n2 over sine theta 1. Theta 1 I've worked out, it's up here. Let's put theta 1 on the solutions. And then I can just solve, so 1.45. So in other words, the refractive index of the let me just reread the question. N1 is the refractive index of the material, and what we've got air up here, haven't we? N2 is air with a refractive index of 1. So N1, the material would have to have a refractive index of 1.5 or greater. Okay, question 13. A sharp image is located 391 millimeters behind a 215 millimeter focal length converging lens. Find the object distance by calculation. Okay, so here's the diagram. We have let's see, what are we told here? The focal length from here to here, that's 215, that's F. The image is 391. No, sorry, the image here is 391. So we want DO, the distance to the object. So this is really a question of just plugging the numbers into this rather nasty equation. We want DO, so I subtract this from both sides and then flip this upside down. I've got DO. Then I have to throw the numbers in, and out pops the answer. Okay. Question 14. Sunlight is observed to focus at a point 16.5 centimeters behind a lens. What kind of lens is it? Well, it must be converging if it comes to a point. What is its power in diopters? Well, because the light's coming from infinity, I don't know if I really say this in the, okay. The point is, I don't really say this in the solutions. If it's the sun, the distance to the object is infinite, isn't it? At which point, if that's infinite, that goes down to 1 over di equals 1 over f. So then the focal length is actually the image to the distance, distance to the image. And so the focal length should be 390, no, hang on, 16.5 centimeters is the focal length, right? Because that's the distance to the image, which is also the focal length, right? They're the same because that is 0. I'm making a bit of a mess of this. Distance to the object is very large, the sun, that goes to 0, di equals f. I know what f is then. I know what f is, and so the power in diopters is just 1 over f, 6.1 diopters. Okay, question 15. A prism, see figure 4, can be used to split white light into its constituent colours. So explain how this works. I'm just going to make a note there about that previous question to add it to the solutions. Okay, refractive index is a function of frequency. We've mentioned this. This is an important point for you to understand. So what happens in a prism, and I've got a nice, I think I ripped off a Pink Floyd album there in figure 4, but what happens is that when the white light enters the prism, it's refracted, right? Because the speed of light in the glass is less than in air. But the speed of light in glass depends upon the frequency. So different wavelengths of light are refracted through different angles. And this disperses the light out into the rainbow that we see. Okay, I think that's the end. That's all of the questions. I hope you understand the fun is the first one is a Gary Larson one, isn't it? Where there's a large eyeball, objects in mirror closer than they appear, and there's a massive eyeball in the mirror. Just kidding. Well, you told us to draw what we see under the microscope. It's a table. Tables under the microscope. Very good. Dinner was ready 2 hours ago. Just where have you been, young man? Oh, there's a 60% chance I was at Suze's and a 40% chance I was at Billy's. Okay, well, this is to do with quantum mechanics, not so much optics, but there we go. Yeah, okay, and I guess that really relates to the next chapter, which is looking at the wave nature of light. Okay?